asked you about the basketball having a horizon, and you said that it doesn't have it.
No, it's a
But if
basketball. Does have
yeah,
a geometric edge, though, doesn't it?
yeah, yeah.
Yeah.
But like I posted a picture in the I guess it's in No Voice. It's just a picture from desert with horizon sort of. But would you call that a horizon? It's not. It's not. It has topography in it. Can that be described as a horizon?
Yeah, that is a horizon. It's the point or the apparent location where the sky appears to meet the land or sea. So, yeah, that is sand.
Mm-hmm.
That is the sky.
But with Bev's description of horizon, that's not horizontal.
Well, no,
That's
but I
not
mean, neither
on a
would there
straight
be
line.
if there was a tree in the middle of there, right?
Yeah. So can the horizon sort of curve then?
Well, it has all sorts of shapes. It depends what you put in the horizon, right?
Okay, good.
You generally
It would-
lean to think about it over water, right? Like the rest has a topographic
Yeah,
horizon.
this is the top. Have you seen this picture, Bev? This is a topographic
The
horizon.
sand one.
Yeah.
Yeah.
Yeah, it's just a load of sand.
Yeah. Yeah.
And
it's just-
and the horizon is conforming to the shape of the sand, and the sand can curve in all sorts of directions.
yeah. But I just remember Bev saying that horizon has to be horizontal. And do you mean flat with horizontal?
The water forms a horizontal plane, and the horizon, when looking over water, is horizontal.
But over land, it's not.
It takes on the shape of the land. The horizon takes on the shape of the land that's forming the horizon.
Yeah, and also that happens with the water.
But the water is a horizontal plane.
Well, yeah, I guess you can say it if there's nothing like tides or anything like that.
Nothing like
Tides. that
tides.
would
How
keep
how do you see the tide at the horizon mark?
When if there's a tide going or coming, then it.
So
would
how
not
do you see the water rising or falling at the horizon?
If you're standing on a beach,
You can't
water
see the
level
water.
would be
You can't see the water rising and falling when on the horizon.
well, the
You
horizon
only
would
know
rise
the
and
tide
fall.
is coming in and out by the rising and falling on the beach.
But wouldn't the horizon be at different altitude?
Why would it?
Apparent? Because the water level is higher and lower.
Not at
depending
the
on
horizon.
tide.
No, at the horizon it's not, is it?
How high are the tides?
Isn't it?
Do you know that?
What?
What is the highest tide on Earth?
The
2
highest
meters,
tide on Earth.
2.5 meters. And the lowest tide, and there are no tides, even on areas with no tides. I think I'm actually where you live, something in that side in Scandinavia. There's some pieces on Earth there are no tides. Do you know that?
Yeah,
Are
we
you
have.
aware of that?
I think we don't have. I don't know if we have any tides over here. So
That's why I posted a
shallow.
video on the other channel. So if you watch that, you can see how the tides are on Earth, and they even disprove the Coriolis effect.
Yeah, I haven't watched the video yet. I'm in the
You must
middle
watch
of
it.
watching.
Very
the-
interesting.
Yeah, I have to put it on my watch list.
So how far north are you?
Me?
Yeah,
Don't
in,
remember the
in Finland.
parallel. I'm in southern Finland.
Okay, would you say you're further north than we are in the UK?
Yeah. Yeah.
Yeah, the most southern point of
Do you-
Finland is further north than the
Do you have a
UK.
camera?
Yeah, I have, but it's not a good camera. It's a Samsung NX1000.
Okay, can't do time lapse of stars or anything. Can you not?
I think no.
Oh.
Not with that thing. There is no option for time lapse, I guess. No.
That's
What
a
do you
shame.
want to do?
Yeah, we're looking for some people to just do some star trails.
Oh. Yeah, I think I don't have a camera for that, but I guess I could check from the internet if someone has done it, because I can search in Finnish. So
Well, just like when you look up and you see Polaris, whereabouts
yeah,
is it?
I haven't looked that much in the stars. I know there's stars, but I don't. If I've seen the Polaris, I see a star in the north that is bright, but I'm not sure if that's Polaris. I haven't checked the charts for stars.
In the north? Because, I mean, it's pretty difficult. It's pretty high, right?
What do you mean high? Like, yeah, it's not like low in the north or in the horizon. It's not low. The one star that I've seen.
Yeah. It's all right if you haven't done anything. I mean,
Yeah, I haven't done much with stars. I should look into it because, I mean, it would be good to know them, maybe.
yeah. Well, most of the ballers tend to use the lights in the sky, don't they? Isn't that one of your proofs? Looking up at lights in the sky proves things,
yeah,
right? To you guys.
Yeah, I think the two rotational points of stars is like hinting to a shape. It would happen on a ball if our model is correct.
On a floating ball.
What do you mean floating?
Well, it's
Just
yeah. What do you think it's doing then?
in relation
Float
to
into
what?
space.
Like, it's in space. In my view,
Floating.
it's not floating. I mean, there's no medium it floats in.
Oh, so things float in vacuums then, or what? What happens? Because
I mean, where would it go? Where should it go?
I don't know. Like, so you presume that things float in vacuums, or is there some other things that seem to give it a weightless property?
I mean, weight. What do you mean with weight?
Well, there's no way really for you to say how a big massive ball can be suspended in nothing. You've just said it's not even in a medium.
Yeah, it's not in a medium, so it can't float.
Right. So what
So
would
it's
you
not
call that
floating in
then?
It's in space.
It's falling,
I mean,
would you say?
where would it fall into?
I don't know. Well, what, like, don't you think the ISS is constantly falling?
Yeah, it is, because it's Earth. It's attracted to the Earth.
Right. So that's not floating though. That's falling.
Yeah, it's orbiting the Earth.
Yeah. And so but you think the Earth is also doing that to the sun, right? So the Earth
it's
must be
orbiting.
falling if it's not floating.
Yeah, it's falling into the sun, but its velocity is great enough to not let it simply fall into the sun.
Velocity, you say? We're getting into
Speed.
weird realms here, aren't we?
Let's
Yeah.
say speed. Yeah.
Yeah, yeah. The speed that we're falling is an extra to a rotational speed that we supposedly have.
Hang on, no, Beth. It is a velocity, though, isn't it? It's an angular velocity because it's a curved trajectory.
Yeah, that's what Rumpus was saying. Because it is a curved, it's a constant acceleration, right? Wasn't that what Rumpus said?
Yep.
Yeah.
Constant acceleration.
Yeah.
Yeah, because it's on a curved trajectory.
Acceleration in what way?
I don't know. I mean, this is your model, mate. We just go off what we're told by you guys.
Yeah, I mean, if you rotate a bucket with water in it, the water is accelerated time outwards.
To the outside.
Yeah, but it's not accelerating
Yeah, but
speed
that
fluctuates with
definitely
the-
doesn't happen here, does it? Because the water stays at your feet; it doesn't go up to your head.
What?
The rotational speed that you just expressed when you said with the bucket with water in it, and you spin the bucket, the water goes to the extremities of the rotation, right? That's what makes it stay within the bucket. So it pushes itself towards the outside of the container. That's basically why Rumpus was saying when we were talking about the gravitron, was it? I can't remember what it was called.
Yeah, it's the thing that gives you G-forces.
Yeah, pushing you out backwards though, right?
Yeah.
But
I don't remember the name of it.
Yeah, we sort of
Yeah,
put that
gravitron.
down to a transference of weight because due to the circular motion sort of pushing you back towards the thing.
But would you say that fairground works on a transference of weight, Mailman?
Me?
Yeah,
The gravidometer?
yeah, the gravitron. You know, the fairground
Oh,
ride that spins.
gravitron. Yeah.
It spins you round, and then either the floor drops away or the ride tilts to 90 degrees. So you stick.
And you
You
can
stick.
be upside down, basically.
Well, yeah, you stick to the outside of
Yeah.
the ride as it spins. So would you
Yeah,
say this is
in and one.
Would you say this is a transference of weight?
Well, it kind of depends. Like, my weight doesn't transfer. My weight is still at the same place. What do you mean with?
Well,
Like if you have a, let's say you put a metal cube over it and you spin that, the weight doesn't move anywhere. It's still there. Isn't
right.
it?
Okay. So if for instance you're in one of the barrel ones where the floor just drops away, so you walk into the ride, you stand against the wall, the ride starts spinning. It doesn't
Yeah.
change on the axis of rotation. It just spins, but it gets faster and faster, and then the floor drops away. Now,
Yeah.
the moment before the floor drops away, your weight was on your feet. What happens
Yeah.
to that weight when the floor starts to move?
Yeah. Like, can we say that if I'm standing on something and then we drop the floor away, what happens to weight?
Yeah, that's exactly what I'm asking.
Well, that's a good question. I don't know if I can answer it because, like if you put a scale there, the scale is falling with you, so you don't measure weight there. But you are accelerating, so there's a force applied to the acceleration. Oh, you need force in order to accelerate, right?
Yeah, but your weight is no longer on your feet, and all I want to know is where's your weight gone? If it's no longer on your feet, where has your weight gone? Because, like you say, if I'm standing on a scale, and I stand again, so I'm standing in the ride, my back against the wall. I'm standing on a scale. The scale is on the floor, so that scale is registering my weight. Now, as the ride spins up, I will weigh the same. The scale will register the same.
It will register more when it's spinning, but
Because I will weigh more
because of the
because of the G-force.
yeah.
Yeah. Right. Okay. Yeah. Right. I stand corrected, Jay. You would weigh more. Okay.
Yeah,
But
but it's a minor thing.
But as this kind of compounds the point I'm trying to make, that as soon as the floor drops away and your feet are no longer on that scale registers zero. So what has happened to that weight? Where has that weight gone? It's no longer on your feet.
Well,
so that weight must have been transferred.
Well, in our paradigm, it's F equals ma, and then you will have the a, which is acceleration, and you'd be accelerating away from the machine.
So the weight, that still doesn't answer the question as to where the weight's gone. An equation doesn't answer the question.
It's acceleration.
But I'm not I've got no impetus into the acceleration. The acceleration is machine driven. It's nothing to do with me.
Well, it's not machine driven if you're not in the machine.
I am in the machine. I'm standing inside the drum, which is driven by the machine.
So you're still inside the drum.
Yeah.
Ah, I
Otherwise,
thought you were.
Otherwise, how would I be stuck to the wall?
Well, have you measured the weight that you're exerting into the wall?
This is what I'm trying to get. Where does that weight go?
I think I understand. I think I haven't heard about the machine that you're using, because I thought that you were just saying that the floor goes away and you'd be slingshotted out from the machine. But
no. You're standing in a drum. You're like a big drum.
Yeah.
And there's lots of people.
There's a picture in the live stream if he wants to have a quick look.
That might actually help a bit. Wait. Yeah, okay. So you're back against the wall, and then it starts to spin, and then you lose the floor. Okay, yeah. Well, if you'd have a scale on the wall also, you could check the weight if it is exerted on the outside wall of the machine.
Yeah, that's what we said initially. Imagine if you go in there and the scales on your feet. So before it starts turning at all the weight would be on the scales at your feet, right? They'd be measuring your weight.
Yeah,
then,
of course.
if you put some scales behind the board behind your back.
Yeah.
Right, and then as you spin, the weight would transfer from the floor scales to the back.
Yeah, obviously.
Right. And as the faster you got, you would get heavier, wouldn't you? There would be more force outwards, so the weight would be transferred to a greater extreme to your back.
Yeah, you could weigh 300 kilos in that thing.
Right. Okay. So the speed difference.
Wasn't that what I said to Rumpus? That was like, yeah.
Yeah.
Oh, okay, that's what I thought. Yeah.
Yeah, but I'm not so sure Rumpus said that the weight would transfer like that, though.
No. I'm pretty sure he said it was something to do with like friction or something, wasn't it?
Yeah. Now, so what we were saying was, like, do you think, what is it that you think that transfers that weight? Now, is it the speed or the rotation? What is the main thing that gives you that force on your back? Like what is it, do you think?
I don't know too much about these things, but I would say it's conservation of momentum.
But it's a constant acceleration, isn't it? According to Rumpus, anyway.
But it's not a straight line acceleration. Your back is not facing the direction that you're moving, sort of. Because if you can't have that on a straight path, never.
Okay, but
you can if you'd be accelerating like 9.8 meters per second squared straight ahead with your back against the wall.
9.8 in that. What you?
Like the acceleration on the Earth downwards is 9.81, was it?
Oh, right. So we had that with Rumpus. That's exactly what we were doing, and we worked out the speed or something that would throw you from this in order to counteract gravity was something. It was about 30 miles an hour or something, wasn't it?
Yeah, 28. I think we worked it out too, wasn't it? 28 miles an hour.
Which speed is it? That is it the speed of the rim?
Yeah, around the outside. Yeah.
Oh, yeah. Okay.
Because the acceleration around the circumference, right? Because that's what you're doing.
Well, not acceleration, but the speed. Yeah.
Well, yeah, but it, like I said, like once it gets up to a certain speed, that would be it, right? But Rumpus seemed to think that that's still a constant acceleration, even at a steady speed, because it's in a like a circular motion.
Yeah.
That it's always a constant acceleration.
Well, it is G-force is like an acceleration, but the wall that you're pressing against is pushing against the acceleration. So
Okay, so
just like the Earth.
when we said that like 30 or 28 to 30 miles an hour or something was enough to counteract like your entire weight, I think, was that what it was? The transference of weight from the floor to the outside is achieved at about that sort of thing. So that is the sort of speed you need to be able to do that. You know, like when they have the motorbike riders that go inside the tube and they can go up the walls.
Yeah, the death ball thing.
Yeah, that was about 28 miles an hour for that. You know, like it's about that visually. It's sort of something like that, right? You'd have to agree with that.
Yeah, well, it also depends on the diameter of the thing. Like if you have like that machine, if you had it so that it's 1,000 miles in diameter, I guess 30 miles an hour would not be enough
to go up the side.
You'd
So
get more.
it's the diameter rather than the speed, you say?
It's both, I'd say. It's the relation between the diameter or the circumference and the speed of the outside thing.
Okay.
Like if you are in a like a merry-go-round and it's 2 meters in diameter, you'd have a certain force outside. But if it's 200 meters in diameter and the outside speed is the same, you don't have the same G-force in that.
But wouldn't that work though? Like if the like, let's call it the radius, right? If the radius stays or gets bigger, but the rotational speed stays the same, that would like greatly the speed at the edge would greatly increase, right? Because the rotation still has to happen at a similar speed.
I mean, if you're talking, well, in this example, did you say 30 miles per hour for the speed?
Yeah, that would be the relationship between the radius and the rotational speed, I'm guessing, for that particular machine, or them sort of things.
So the distance that the outer rim travels, basically, is the speed. Yeah.
Yeah. So if you imagine that if that's like 10 meters and you go in at 33 and then you increase that radius length to 20 meters but keep the actual rotation speed the same, the outside rim speed would be increased greatly, right?
Yeah, that's exactly what I said. That if you increase the diameter, you have to also increase the speed of the
you have
outside.
to slow the speed down, right? Because otherwise, if you increase the speed and increase the diameter, that would be exponential, right? That would be massive rim velocity speeds, wouldn't it?
No, but my point was that if you have 10-meter diameter and the outside is traveling 30 miles per hour, you would get a certain G-force. Let's say it would keep you on the wall.
Yeah.
And then you have the diameter at 20 meters. You can't have the same effect with the outside of that 20-meter thing going at the same speed. You'd have to increase the outside speed.
No, just increasing the diameter would increase the speed.
Increase the speed.
Yeah, it would increase the speed. I mean, I think we're talking about two different things now.
No, I think we're talking about the same thing, only you've got the opposite idea.
Yes.
To happen.
I would agree.
Yeah, well, my view is that if you increase the diameter, you have to increase the outside, the speed that the rim is going.
Yeah, but by increasing the diameter, you are increasing that speed, because the extreme outside of that diameter has to travel further
at
the same rotational speed
of arc.
Yeah, and that basically is also my point, that if you increase the diameter, forget the like, how can I say it? When you increase the diameter and you keep the speed, the rotational speed in decrease the same, obviously the outside would move faster, because it would.
Yeah.
But that's exactly my point, that if you wanna stay, like if you, let's say you have that thing, it's 10 meters and the outside is traveling at 30 miles per hour, and you increase the diameter to 100 meters, would you still be able to stick to the wall with that speed?
Too right.
If-
That'd be
If
dangerous.
if you're maintaining the same rotational speed, then the outside edge of that 100-meter diameter is moving faster. So yes.
So what you are actually saying is that if I have a bucket with water and I have a 1 meter line attached to that bucket and I rotate it like, what should we say, 2 rotations per second? Is that fair? Would that be enough?
Go ahead,
Or
yeah,
5
yeah.
rotations? Let's say 5 rotations per second. And the water
Jeez, what
sticks
you...
to
Steady on. You'd
Yeah.
be hurting yourself.
well, whatever rotations per second you need for that water to push against the bucket. Your point seems to be that if I have the longer length the rope is that I have, the higher g-force I'm exerting with the same rotational speed. Is that fair to say?
Yeah, that's what we've been saying. It's a faster speed at the rim.
Yeah, but can that be demonstrated?
Yeah.
I would like to see a demonstration.
Right, so basically what I was trying to get to was the fact that there is a relationship between the radius and the rotational speed of that thing that ends up giving you around about a 30 mile an hour rim velocity. Now that 30 mile an hour rim velocity is enough to transfer the whole of your weight through 90 degrees.
Yeah, to the like a vertical. No, not vertical.
Yeah.
Get my
The vertical
get
behind
my
you. The wall.
directions mixed up. Yeah.
Yeah.
The wall behind you.
Yeah. So how did you do you have a calculation for that?
I don't know. Rumpus did it. We did a video when Rumpus worked it all out, and Rumpus and Tony went through it. We were just
I just wanted to know what happened to your weight once the floor dropped away. Where did your weight go? You mentioned earlier, Mailman, that the weight, your weight is how did you? I can't remember how you phrased it. Actually, you said that the acceleration pushes you out. Did you say the wall pushes back?
No, the wall is stopping, like how could I say it? It's resisting you from accelerating outside.
It's a resistance. It's not like a an equal and opposite force effect. Do you see what I mean? That your weight is now being pushed out, so that wall is pushing back at you. It's a resistance rather than a pushing back mechanism.
Yeah, it's stopping you from accelerating.
Yeah,
right.
Like
so
resisting the force. It's resisting the
resisting.
force.
Yeah. It's not. It's in no way pushing you back towards the center of the gravitron. No.
Well, I would say that it's just resisting the you going out.
Yeah,
Right.
I mean, it would be silly to say that the wall had a force that was pushing back as an equal and opposite.
As kind of against the centripetal force. So the centripetal force would be pushing in opposition to the centripetal force.
to the centrifugal.
The centrifugal pushes out. Yeah, sorry, yeah. So, yeah.
Oh, yeah.
Yeah.
Yeah, centrifugal pushes out. I haven't looked into centripetal that much. I mean, I have to look into it more. I don't know my forces that well, to be honest.
But you'd agree that there's no way the wall of the fairground ride can generate a force that pushes in opposition to the force that's pushing you outwards.
Well, I would have to look into it more, what it's like, how it's described. But I mean, if it's resisting something, then I guess it kind of is force. But I don't know how you'd say it.
Yeah, you sort of get into dodgy realms of defining forces at this point, don't you?
Yeah.
Yeah.
Well, yeah. It's like G-force is not a force. It's emergent force or pseudo force or
Pseudo force, yeah. We
Yeah.
like that one, pseudo force. That's a good
But you
good
just,
definition.
yeah,
It goes
it's
with
caused-
pseudo
it's caused by-
Ramonian force base, doesn't it? kind of
Yeah.
goes hand in hand. You get a pseudo force from pseudo Ramonian force base. It
or you
kind
get
of
pseudo
fits together.
Yeah, you get pseudo force from someone spinning a bucket. So
Well, no, because you're putting the energy into that centrifugal force, aren't you?
yeah,
You are
So-
creating a centrifuge by spinning the bucket.
yeah. So there's
So
two
you are
forces.
putting the energy in. You are creating that force that's sticking the water to the inside of the bucket when you spin it.
Yeah, basically. But I'm using a force that's creating a force.
But you are putting the energy into the system.
Yeah.
So you can
I put
create
it-
the force by putting the energy into the system.
Yeah, I have to
Well, there you go.
put energy into
That-
it. Yeah.
Yeah, that is the equation finished. So you are putting energy in. You are creating a force. The force has an effect. End of story.
Is there a? I'm wondering with that. Can we measure the energy that I use to spin the bucket and the energy that the water has to the bottom of the bucket, or the whole fucking thing, the bucket and the water? Can we measure
probably.
all the forces in that thing?
Probably.
Do you mean the weight, or what do you mean by the force in the bucket?
Well, the G-force, but I don't know how you'd.
I don't
Yeah,
know.
I don't know. You'd need to.
Is there
you'd
a
need to-
G-force meter anywhere that we can, especially one that we can
Yeah,
put in
well,
water?
well,
I remember.
that's-
I remember when I was at school, we had Newton meters, like little springs,
Yeah.
two springs that pulled a gauge apart in the middle. So
Yeah.
you could hook the handle of the bucket onto one end of the Newton meter and the string
Then
onto
you
the
can-
other end of and just see how many newtons are being used as you swing the bucket.
Just like a
Easy,
weight
job done.
scale thing, right?
Yeah,
Yeah,
just
yeah,
a scale.
yeah,
Just
yeah,
a scale
exactly.
on the string.
I remember
Yeah.
that.
Yeah, exactly.
But then again, it's forces and energies and
Just measuring an
It's not
increase
true.
in weight, though, right? You just
Yeah.
got a scale.
yeah.
Yeah.
Well, there's
But I
no doubt
wonder-
you could work out how many calories you're burning as you do
but
your
then-
experiment, and that's another way of working
Yeah.
out transfer of energy.
We're
So
not.
But
We're not
then-
going to say that an increase in weight is an increase in force. Therefore, directly correlate weight with force, are we? I mean, it's a little bit dangerous, that, isn't it?
To say in weight is force.
Yeah.
Why is it dangerous?
Well, like, is that what you're willing to go with? So then, therefore, would that be?
Well-
Would you say gravity, therefore, is weight? And the
Well,
more weight
I mean-
something has, the more gravity it has.
No more mass it has, but it's a slippery slope with mass, at least with QE. I give you that.
Well, no, I'm just thinking for you. I mean,
I mean,
directly correlating weight to force. is
it's
a bit. It would be for you. Would be a bit tricky to hold that one, right?
And then not directly, of course.
I've got a little bit of a question that's been puzzling me about weight and stuff, right? But how much does somebody?
Domestic.
Sorry.
You're domesticated primate. I just saw your picture there.
Which picture?
Your
Oh, my
PFP.
avatar. Yeah. Hi, how you doing?
Yeah, I've been picking you sometimes.
Sorry?
But it's we've had some issues with each other.
You've been triggering him, DP. You've been triggering him with your memes.
Yeah, we've been doing it both ways, I guess.
Whereabouts?
I'd say it's fair. I guess in Nathan's or Syrinx's or Betty's.
Oh, I've not been in there for ages.
I haven't seen you around there.
No, I got banned from there, didn't I?
By Righteous.
Yeah. Well, no, actually, it was Betty that banned me. That actually kicked me from the server because I've got a problem with the way Righteous runs the server. The way he moderates it isn't fair. So I kind of pointed this out to Betty. Betty took issue with it. We had a mad afternoon sending DMs backwards and forwards, and she got to the point where it was either I apologise for Righteous's behaviour and she wouldn't kick me from the server, or she kicks me from the server, and I'm like that. I'm not begging to stay on your server, Betty. You know. It's not that important to me to lower my standards to beg for you to allow me to be in there. So she kicked me. So who are you over there then?
Question. I'm Moleman over there, but I've had other names. I don't remember what I was called. I was qualified epileptic.
Sorry?
And qualified epileptic.
No, don't remember that one.
Yeah, but I don't remember what I was with. Now I'm Moleman.
No. This must have been a while ago. Was it with when?
Yeah, like months ago, I guess.
Yeah.
Yeah, but you had a question.
I
told you.
Oh yeah. Right. You got an astronaut.
Yep.
Right. He weighs. I don't know. You work in kilograms. We work in stone over there. So he weighs 14 stone. Gets in his rocket. His weight is accounted for with the calculations, with the fuel and the velocity of the rocket. Every gram counts. Yeah.
Yeah.
So his weight is accounted for in this rocket.
Yeah.
Right. He's sent up in his rocket. He goes through the Kármán line. He bursts into space, and all of a sudden he becomes weightless. Completely weightless. Nothing in space has weight. Yeah.
Well, depends how far you are. Like.
Right. Okay. So.
Like the ISS is not just floating; it's traveling because
it's falling. Yeah.
Yeah.
So, is that a weightlessness?
In space, like in ISS?
Yeah, is the ISS weightless in its fall around the Earth, and the astronauts are weightless within the ISS falling around the Earth?
I mean, I think it's like a 0G plane. Depends on the like in a 0G plane you would have no weight on a scale, right?
Okay.
So the ISS is
strange you go to the plane.
Huh?
What? When you say 0G, right? I mean, is that what you mean? In a plane, you can get to 0G. So you're saying that you can get rid of gravity by falling, right?
Yeah, well, if you're accelerating down or slowing down going up, your weight changes.
Okay, so it's an acceleration now, not a weight. gravity?
Well, a scale stops the acceleration when you're standing on, or when you're standing on Earth. You can't accelerate because there's something in the way. So you
Well,
exert
just a
force
bit
on
before it was a weight, though.
What? Weight was weight?
Yeah. And now you're saying that gravity's an acceleration.
Well, I don't follow now.
Well, when you were doing it in the book, and we had in the bucket, and we were spinning a thing around, and we had a little Newton meter on it, then we were measuring a weight change.
Yeah, of
And
course.
you said that was gravity. And I said, you've got to be careful saying that weight and gravity are the same thing. You're very dangerous. And then now you've just said that gravity is an acceleration.
So you've succumbed to the very danger that we warned you, or that Bev warned you about.
Well, I think I don't catch the issue. Like, weight is like I don't know how to say it. Like, if you're standing on a scale, you register weight, right?
Yeah.
Which is
I don't know how I would word it. Maybe resistance to acceleration. Like if you have a car and your front of the car is pushing to a scale and you try to accelerate, the scale will have a reading. But if you don't have the scale there, you would accelerate. So the scale is resisting that acceleration by being there. Does that make sense?
Anyway, nice to meet you.
I mean, it sort of makes sense to me, but
Well, first of all, you had the water in the bucket was a force, and then something in the 0G plane has no weight.
yeah, because you're accelerating down. So yeah, there's nothing to stop the acceleration over there.
Right. Okay. Anyway, going back to my original question, right?
Yeah.
Was that things falling around the Earth in an orbit apparently have no weight?
Yeah.
Right. So the sun, the Earth is apparently falling around the sun in an orbit, and would have no weight. It would have no weight in space. So
yeah, you can't really like
well, surely
measure the weight.
surely it's just an equivalence of scale. If one thing happens at one scale, i.e. the astronaut inside the ISS falling around the Earth has no weight.
Yeah.
There is no gravity. It's just an equivalence of scale. All you got to do is scale it up. The Earth is apparently falling around the sun. So therefore, it would have no weight. It would have no gravity. So how can it bend? How can it put a bend in space-time if it has no weight and no mass because it's falling around the sun?
Well, I'd say it has mass.
But we've just established that something falling around the Earth doesn't have that weight.
Yeah, it doesn't have weight, but it has mass.
A constant acceleration of any sort of speed, haven't we just sort of worked that out? If there's no barrier, it'll just fling it off, right? You needed that wall as a resistance to stop you from moving in an outward direction. Because like it's to stop that straight line path, right? You did say that.
Yeah. You need to have the bottom in the bucket, otherwise the water would fuck off.
Well, that's not like that with your presupposed balls, is it?
Well, I mean, I don't know how you'd compare those two. There's no rope from sun to the earth.
Yeah, you're right. One of them's it's just theoretical, right? There's no way to.
Yeah, there's no bucket holding the water on the Earth either. So why doesn't it just fuck off into space with the centrifugal
Well, the
force?
water has weight because, yeah, it's on Earth and we have gravity. So it's trying to get inside to the Earth, sort of, but yeah.
Yeah, but even according to your scientists, gravity is the weakest force. So how would it overcome the centrifugal force that's generated by the motion around the sun?
Well, has someone calculated the G-force that the Earth's
Well,
orbit
they don't
has?
need to do the calculation, do they? Because the centripetal force would overcome the gravitational force because the gravitational force is said to be the weakest force. So how could the weaker force overcome the stronger force?
Stronger force being
Centripetal.
Centrifugal.
Centrifugal, yeah.
Well, I mean, centrifugal force. I mean, you can have centrifugal force as small as you want or as high as you want, depends on the speed. Doesn't it? Like, if I rotate a bucket 0.0001 revolutions per year, the centrifugal force would be very small.
Depends how long your bit of string is, doesn't it?
Well, even if it's 1 millimeter long, if you rotate it 0.00001 revolutions per year, it's quite small force, I would say. So small you can't even do it. I mean, you can basically get centrifugal or centripetal force as small as you want. I don't know how small you can get magnetism to be. I guess you can have that as like a small or weak force too. I don't know what magnetism, like how they use it in describing it. I haven't looked.
Yeah, I'm sure you can
Much
get different
into it.
strengths of magnets, can't you?
Well, yeah, obviously. Just depends on the magnets that you're using.
Yeah, absolutely.
Yeah, but sorry, I have to get back to work. I've been doing nothing for an hour here.
No worries.
Yeah,
No worries.
but I'll come back later.
Okie dokie.
Oh, good to have you in.
Yeah.
Yeah, take it easy.
Bye. Yep, you too.